Hello everyone, welcome to the sixth problem session of CmpE 150 course. Today we will solve 6 problems about while loops. Let me begin with the first question. This question wants us to write a program that takes an integer n and prints the sum of the squares of the first n natural numbers, as you can see in the examples. So if I give 3 as the number of n, I get 14 as the sum of 1, 4, and 9 as the squares of the numbers starting from 1 and to get 3. So let me first take a number n, and then I write while n is greater than 0, and I should also define a number for the initial sum as and I set it to 0, and s is incremented by the square of n, and n is decreased by 1 for all these operations, because I start from the initial assumption of n equals 3, and then I should take 3 to 1 by the sequence. So that's why I am decreasing the value of n by 1 at each step. So let me continue and print s here. So what I have done, I have written a while loop for this barrier. So if I have 3, then it adds 9, and then the number of n is decreased by 1. So I get 2, and I add 4 here, and I get 1, and I add 1, and I reach 0 here. And while the n is greater than 0, this loop can be operated. But if I have 0 here, then this loop is broken, and I continue with the next line of code. So that's why I can print my sum of squares here. So let me check this. And it gives me 14 for the input of 3. And for the input of 5, I should get 55, as you can see. So let me continue with prime factorization question, the second question. This question wants us to write a program that takes an integer and its prime factors in a single line, as you can see. So if I give 36 as an example, I should get 2233. So let me take an integer n again as an input. And I will define firstly a for loop for the divisors, for the prime numbers here. It is for I in range. I will start by 2, and it should include the number of the value of n. So I write n plus 1, and while the remainder of this operation is equal to 0, then I can print I, and I should define the value of n by n divided by I. So the logic behind this method is that I start initially by 2, so it is the smallest prime number. So for example, if I give 36 here, then it is divided successfully by 2, and I print 2, and I divide it by 2, so I have 18 here. If I give the number 18 for this loop, and I use the number 2 here, so this while loop can be operated. And I print also the second 2 here, and I get 9 from this operation as 18 divided by 2. And if I give 9 here, this while loop cannot be operated because 9 is not divisible by 2. That's why I will continue with 3 by taking I equals 3 from the upper for loop. I have 3 as I, and n is equal to 9. Then this while loop can be operated, and I print 3. Then 9 divided by 3 is 3, and I continue like that until I reach 1. And as you can see, I cannot operate this loop when I reach the last number. So this can give me all of the prime factors starting from the least prime factor. Then it should give me the maximum prime factor here. So I can operate this program. I give 36, and as you can see, it gives me 2 2s and 2 3s. If I give 32, it should give me 5 2s, as you can see. So this program can be operated successfully, as you can see. The next question, actually the next two questions are about least common multiple and greatest common divisor operations. So I should take two positive integers in both of these cases and print their least common multiple or the greatest common divisor numbers. So I will start by taking two inputs. And for example, if I have 6 and 12, the least common multiple is 12. So I can start with the assumption that 12, so the greater number is equal to the initially assumed least common multiple. So for example, if I give 6 and 12, the initially assumed least common multiple is 12. So if I check that 12 is divisible by 12 and 6, then it can be the least common multiple here, because least common multiple can have the minimum value of the greater number for two given integers. So that's why I will check if A is greater than B, and if it is true, then I will define a number C, and C is equal to A, else C is equal to B. So let me continue by writing a while loop here. So while I can divide C by A without any remainders, and also by B without any remainder, then my least common multiple is equal to C, and I can break. Sorry. I have done something stupid, sorry. So I will operate this while loop initially by an infinite loop. So if I write while true, this will operate infinitely. So if C can be divided by A without any remainder, and also if I can divide C by B without any remainder, then I can say that least common multiple is equal to C, and I can break this infinitely operating loop. And else, this condition cannot be sufficiently given. So I can increase the value of C by 1. So I am eager to take the least common multiple. So it should be the least number. It should be the minimum number. So I can go by 1 by 1. So if, for example, if I have 12 and 18 as given in this example, I check that initially if 18 is the least common multiple, and I assume that C is equal to 18, and I give these numbers to this loop, and it checks that the divisibility of 18 to 18 and 18 to 12, and 18 to 12 is not isn't a division operation without a remainder. So this if condition is not sufficient, so I can add 1 to 18, so I get 19, and it goes on like that until I reach 36 as the number of C. So if I have 36 here, then I can divide 36 by 12 and 18. So both of the numbers can be divided with this number. So I can clearly say that this number is the least common multiple here. And at last, I will print least common multiple. Let me check. I'm checking these examples. and it gives me the correct results. So let me continue with the greatest common divisor question. I will not remove my program here because it has a similar logic. So what I have done in the previous question, I have assumed that the minimum possible value of least common multiple can be equal to the number which is greater than the other one. So greatest common divisor has a similar logic, but I can assume that the smaller number can be the greatest common divisor because, for example, if I have 12 and 6, the greatest common divisor is equal to 6. So I assume that, and so it cannot be equal to 8 or 9 because 6 is not smaller than these values, so it cannot be divided by these values without any remainder. So I assume that the smaller number now is the number C. So I change these values, as you can see. If A is greater than B, then C is equal to B, and else C is equal to A. So while true, I will check the divisibility of A and B to C. So what I have done in the previous question, I have checked the divisibility of C to A and B. So I should change these numbers. So C is now A is now C is now B is now C. And the greatest common divisor is C, and I change this variable also. And I should decrease one now because in the previous question I have incremented the value of C to reach the least common multiple, so to reach a minimum value. So I have increased these one by one, but now I should take the greatest one and stop there. So that's why I should decrease the value of C. So for example, if I give 36 and 16 as an example, the A is 36 and B is 16 here, and I assume that the smaller number is equal to C. So here 16 is equal to C, and I checked the divisibility of both of these numbers to 16, and I cannot reach this correct condition for both of these expressions until I reach 4. So I operate starting from 16 until I reach C. So I think that this program should give the correct results. I check if it does that. Okay, wonderful. I get the true values. So let me continue with the fifth question. This question wants us to write a program that takes a positive integer and prints the sum of its digits. So let me take an integer x, and while, and also I should find a sum and set the initial value to 0. While x is greater than 0, then I should increase the value of s by the values of digits. So I can start with the last digit. For example, let me take this number as an example. So the last digit is 1 here. How can I reach the value 1? I can check its divisibility by 10, and 1 is the remainder here of the operation 2021 divided by 10. So I can write x remainder 10, and it gives me the remainder of the expression I have explained just before this code. So then I should change the value of the variable x. So I should define it. For example, here I should define it as 202. So I should remove this number, this digit, the last digit, for every operation until I reach 0. And if I reach 0 as the value of x, this loop can be broken and terminated. So I can print the sum confidently. So to do that, I write x minus x remainder 10 divided by 10. So what I have done here, for example, for the first operation of this number, I have 1 as the remainder of the x remainder 2 operation, sorry, 10 operation. So I subtracted the value 1 from 2021, and then I have 2020. And if I divide this number, I reach 202, as you can see here. So then I get 202 as the new value of x, and I take the remainder of the division of 202 by 10, and it is equal to 2. And then I add it to the sum of digits, and then I subtract the value 2 from 202, and I get 200 here. So I get 20 from this operation, and as you can see, I have 20 here. I put 20, I get 2, the remainder is 0 here. So I can get 20 divided by 10 here as new value of x, and it is equal to 2. I get 2, as you can see, on the first digit. And then I check that 2 is greater than 0. 2 remainder 10 is equal to 2. And I add 2 here. So then I get 0 here. So the new value of x is equal to 0. And I should break this while loop because x is not equal to 0 here. So I can go on with the printing operation. So I print s as the sum of digits. Let me check. It gives me it gives me the number as a float, so I can write int s here. Yes, it gives me 5. Let me check this number. It gives me 36. If I add 17, it should give me 8, and it gives me 8. So this question is completed. Now I can continue with the sixth question. This is our last question, and it is about Taylor series. So Taylor series is an assumption to calculate some different the values of several different functions, and the Taylor series expansion of the exponential function e to the power of x is given in an expression, as you can see here. And this question wants us to calculate the value of the mathematical constant e using the Taylor expansion of the exponential function. So let me begin with taking two integers as inputs, x and n. And I can also define a function above these inputs because I will need the factorial of some numbers in my program. So I should define a function to calculate the factorial of a number, for example, I. So while I is bigger than 0, I write f is equal to 1 initially, and if so while I is greater than 0, f is multiplied by I, and then I is not incremental, decreased by 1. So this should return f as the value of a factorial. So let me test it. factor, for example, 5, it should give me 120, and it gives me 120, as you can see. So let me continue. What this Taylor series wants us, this Taylor series can assume the approximate value of e to the power of x for the given x and n. And it takes the sum of these numbers starting from n equals 0. Then it goes actually infinitely to take the nearest value of the Euler's number, the E constant. But in this question, we will not go infinitely. So I will give a number n, and I will stop there. But it should give us a really approximate number to the first 5 or 6 digits after the decimal point of E. So while n is greater than -1, because here actually on this step we have n equals 1, and here n equals 0 actually. So these are not on the example here, but there are actually some secretly written expressions on these terms because it starts with the initial number of n equal to 0 on this sum operation, and this is 0, this is 1, this is 2, this is 3, and it goes on like the indexes of a list in Python. So that's why I am writing this while loop to be operated if n is greater than -1. So n can be n can take the value of 0 as a minimum value. So let me define this number, and I can actually define a sum variable as s, and it is initially equal to 0, and s is increased by x to the power of n divided by factor n. And then I decrease the value of n by 1. So if I take, for example, 3 as n, then I take this term, and then I decrease the value of it by subtracting 1 from it. So I get 2, and I get this term. If I have n equals 1, I have this term. I have this term when n equals 0, and when n equals -1, this loop cannot be operated, and it is broken, and then the program goes on with the next lines to be operated. Then this s is actually our sum of an approximation of e to the power of x here. So I need the number of the value of e. So I should take the root of this value and the roots the root's upper number should be equal to x. So I can actually write print s to the power of 1 divided by x. So what this operation does, this operation takes the x root of s, so our sum. So this is our sum, and the x root of our sum is equal to the Euler's number e, the mathematical constant. So let me check for some numbers and make some assumptions. So I can give 3 for x, and I can give a large number for the value of n, because for the approximation of e to the power of x, this value should be going to infinite, to an infinite number. So I can give, for example, 500. And as you can see, I can have the first 5 digits after decimal as given in the example here. So if I have 15, I can give 800. And as you can see, I have a very approximate value of Euler's number as the mathematical constant E. So let me repeat what I have done on this question. First of all, I have defined a factorial function, and I have implemented a while loop. So the initial factorial is equal to 1, and while I, the given number, is greater than 0, then I multiply this number by the previous factorial. So if I give 5, for example, the new value of f is 5, and then I is 4, and then I multiply 5 by 4, it is 20. I multiply it by 3, it is 60. I multiply it by 2, it is 102, it's 120. And I multiply it by 1, it is again 120. And while I is 0 here, it cannot be operated. So the value of last f is returned from this function factor. I take two inputs, x and n, and I set the sum of this value, the initial value of this Taylor expansion, Taylor series expansion to 0. And while n is greater than -1, because this is the 0th step, this is the first step, this is the second step, so n is equal to 2, n is equal to 1, n is equal to 0 here, and this sum formula takes the value of n initially by 0, and it goes on infinitely to an infinite number to really have the nearest value of mathematical constant E. That's why I'm using this operation. And I add the nth power of x divided by factor, and then n, so nth factorial, as you can see, x to the power of 2 divided by 2 factorial. And I decrease the number or the value of n by 1 at each step. So, for example, if I give any x and give the n as 3, this is my last step. So I start with the last step, then I take the number n equal to 2, and then 1, and then 0, and then it is -1, it lost. And if it is -1, it cannot be operated. So it goes on with the next lines of code, and it sees the print function. This is the last line of my code, and this is the xth root of s. So I take the xth root of e to the power of x, and it should give me the value of e. And as you can see from the on the examples I have tried on this program, I can get some approximate values of the real value of Euler's number, which is the mathematical constant E.